Now for today's workshop, I would like to present Alexandra Zamboulis. Alexandra is a postdoctoral researcher in the group of Professor Bikaris at the Aristotle University of Thessaloniki, working on polymer synthesis and characterization. Of course, she's the project manager of REDONDO, our project manager, and today her presentation will be about exploring the potential of tannic acid as a natural filter for HDPE. Alexandra, the floor is yours.
Hello to everyone. I'm very glad to be here today. I would like to thank everyone who has participated to the workshop. So, as Kostas kindly said, I will present some work that has been performed at the Aristotle University of Thessaloniki in the context of REDONDO on incorporating tannic acid in high-density polyethylene. So the Aristotle University of Thessaloniki is in Thessaloniki, which is a city in northern Greece. It's the largest university of Greece, and it has approximately almost 90,000 students. This is the School of Chemistry, and our labs are here in the top floors of the new building. And okay, this is the square in front of the School of Chemistry where we had, now it has faded a bit, the biggest periodic table for a little while. So tannins are natural polyphenolic compounds that are quite widespread, not as much as cellulose or lignin, but still. And they are very structurally wise, very diversified. Their common characteristic is that they are heavily hydroxylated, and more specifically, we have a lot of phenolic hydroxyl group. Common uses are in the leather industry to turn animal skin into leather. Tannins, of course, there are a lot of tannins in wine and black tea linked to the particular taste and color, and the tannins are used in pharmaceutical and food industries. We can classify them into three main categories based on the repeating scaffold. We have the hydrolyzable tannins, which contain gallic acid moieties. We have fluorotannins, which are derivatives of fluoroglucinol, and also condensed tannins, which are derivatives of flavan 3-ol. Now, tannic acid is categorized in the hydrolyzable tannins. It is an ester of glucose. So here you have the central glucose unit, which is esterified by 10 galloyl groups. So tannic acid is not a pure compound. It is a mixture of different esters with a different number of galloyl groups. But on average, we have approximately 10 galloyl groups per glucose molecule. Tannic acid is isolated from tara pods. So tara is a small tree in South America. From its pods, inside the pod we have some pins, and also from gallnuts from oak trees and sumacs. So gallnuts are these round-shaped thingies. Actually, they are a result of a symbiote between insects and trees, and they are formed as excrescences when trees are attacked by insects that deposit their eggs on the trees. So they are grown on the young branches or on the twigs of the trees. Both theropods and gallnuts have been used by local traditional societies to treat different conditions. So tannic acid is hydrolyzable and biodegradable as an ester. It's widely available, it's affordable, environmentally harmless, and biocompatible. Also, it has been found to have antibacterial, antioxidant, antiviral, and anti-inflammatory activity. When it comes to polymers and the polymer composites, it is used because of its numerous hydroxyl group. It is often used as a cross-linker, either with a natural polymers such as chitosan to improve mechanical properties, or also to cure resins. In the context of Redondo, the general idea is to valorize biomass to produce environmentally friendly fillers. So we have had the examples of lignin and cellulose earlier. And here at AUTH, we used tannic acid to confer antioxidant properties to high-density polyethylene. And we further, beside the antioxidant potential, we further examined the impact of tannic acid on the other properties of HDPE. Materials were readily prepared by melt mixing at 190 degrees. The materials were mixed for 10 minutes. And with the exception of the composite containing 1% of tannic acid, which was light brown, most materials were dark colored, almost black. And the tannic acid contents that were studied were ranged from 1 to 20%. Infrared spectroscopy was used to study the materials, and of course we can see the intense absorption bands of polyethylene, but also with a closer look we can see that we have some characteristic absorbencies of tannic acid, like the ester. Here we can see the ester bond and the aromatic rings that confirm that tannic acid has been successfully incorporated in the HDPE matrix. Differential scanning calorimetry evidenced a slight shift to lower melting temperature with increasing tannic acid content, and also the composites with 1 to 10% of tannic acid exhibited slightly higher melting enthalpies and also a higher crystallinity degree. This could potentially be attributed to some nucleating effect of tannic acid. Nevertheless, generally speaking, HDPE is a polymer with fast crystallization kinetics. So we will investigate more about this potential nucleating effect by studying non-isothermal crystallization. The crystalline structure of HDPE is not affected by the presence of tannic acid. When it comes to the mechanical behavior, Young's modulus is a bit increased or retained with the incorporation of tannic acid. But on the other hand, the stress and break and elongation and break steadily decrease proportionally to tannic acid. And here we have some photographs from scanning electron microscopy from the fracture surfaces of the composites. And we can see that while with the first, in the low tannic acid content, we have longer fibrils on the fracture surface. When the tannic acid content increases over 15%, the fibrils are much shorter, indicating a brittle material. Thermal stability was further studied. So we can see that tannic acid, which is here, this purple line, purple curve, is less stable than HDPE. And the onset of thermal degradation decreases proportionally with increasing tannic acid content. The temperature of maximum degradation is not much affected. So overall, we can say that the composite retained a good thermal stability. Now, when it comes to the antioxidant properties, which was the main focus of this study, they were assessed by the DPPH method. So we have the DPPH method is based on the 2,2-diphenyl 1-picoyl hydrazine radical, which is a stable radical under ambient conditions. And in a solution, it gives out a nice purple color, and it absorbs at around 517 nanometers. In presence of antioxidant compounds, the radical is destroyed, is scavenged, and therefore the absorbance is decreasing. So by measuring the absorbance, we can calculate the radical scavenging activity of our composites. So Here in the bottom of the graph, we have neat high density polyethylene, which has a negligible scavenging activity. Here you can see the composite with 1% of tannic acid, which is already showing good antioxidant activity. And here are all the other ones. So we did a second set of experiments with more frequent measurements. And you can see that the materials exhibit exceptional antioxidant properties, with the material with the highest tannic acid content scavenging 85% of the radicals in 30 to 45 minutes. This antioxidant activity is due to all these phenolic hydroxyl groups that are free and have not been affected by the preparation of the composite. So to conclude, tannic acid was successfully incorporated into high-density polyethylene up to 20% by weight. DSC evidenced a facilitate crystallization, but further studies are ongoing to confirm this observation. Mechanical behavior tends to deteriorate with tannic acid content. Thermal stability was satisfying, and the composite exhibited excellent antioxidant properties. So further studies on aging and on oxidative aging, and if it can be delayed by the presence of tannic acid, are ongoing. So before closing, I would like to remind about the REDONDO project, which aims to synthesize reversibly cross-linked polyethylene using green and bio-based additives to have even better improved properties that will be tested for pipes, in pipes and cables. I would like to thank everyone that has been involved in this work, and so this is all our lab, and more particularly Mirto Tara, Christina Samioutaki, Dr. Evangelia Tarani, and Professor Dimitris Vidalis. And of course, we would like to thank the European Union for the funding. If you want to learn more about the REDONDO project, you can, we have our website, you can subscribe to our newsletter, and of course, follow us on LinkedIn. So thank you everyone for your attention.
Thank you so much, Alexandra, for your presentation. And with the end of this presentation, we reach the end of this online workshop.